Dear professors, I'm the reporter Zhang Feng. Graduate student Liu is my classmate. Professor Zhao is my advisor. I come from College of Information and Computer, Anhui Agricultural University. Thanks for watching this video. I would like to present the paper, Adaptive Trajectory Tracking Sliding Mode Control for Agricultural Tracking Robot. Considering parameter uncertainty in this video, my presentation will cover these four aspects: introduction, modeling, experiments, and conclusion. Firstly, I will make a brief introduction. With the advantages of small size and large range of movement, the agricultural tracking robot has received great attention in the fields of farmland environment monitoring and agricultural product picking. It is one of the key technologies for ATR to carry out a stable and precise control. However, the conventional linear control method is difficult to meet the requirements of practical agricultural applications and high precision control performance. The feedback linearization method has no guarantee of robustness when the system is uncertain and disturbed. The neural network control method has a complex control algorithm. PID control method has a poor control effect on nonlinear and structure uncertain systems. Our work can be summarized as follows. In this paper, an adaptive integral sliding mode switching function with variable tilt parameters was constructed from the perspective of control strategy, based on which an adaptive sliding mode tracking control, composed of equivalent control and switching control was proposed, which could feedback the speed and pose error of the robot to the variable structure control, and then the kinematics relationship was used to decompose the expected speed of the driving wheel. At the same time, theoretically, the accessibility and stability of the control method were verified by analysis, and the effectiveness of the control method was verified by simulation and experiments. Secondly, I will describe the modeling. 1. Pose error mode for trajectory tracking. Figure 1 shows the top view of the ATR's geometric structure and the schematic diagram of the coordinate system definition. According to Figure 1, the kinematics mode of the crawler robot is given by equation 1. The actual pose of ATR is P equal x, y, theta, and the expected pose is PR equal xr, yr, theta, t. The pose error of ATR is shown in Figure 2. 2. Design of adaptive sliding mode trajectory tracking control. In order to realize the adaptive sliding mode trajectory tracking control of ATR, the ASMTDC of variable integral switching function is constructed. The ASMTDC control system is shown in Figure 3. A design of switching function. The sliding mode switching function 2, based on the variable tilt parameters, is designed according to the characteristics of the differential equation 1 of pose error. B. Design of sliding mode control laws. The total sliding mode control law is U equal U eq at USW. C. Stability analysis. the accessibility of the boundary layer, and the stability of the system equilibrium point in the boundary layer are analyzed to prove that ASMTDC can control robot tracking trajectory to converge to the equilibrium point. That is, the tracking pose error tends to zero. Theorem 1. Considering the system equation 1, construct the switching function according to equation 2. If the sliding mode control law shown in equation 3 is adopted, the system described in equation 1 will reach the sliding mode boundary in a limited time. Theorem 2. If the system described by equation 1 reaches the sliding mode boundary in a limited time, construct the switching function according to the equation 3, where dt is a bounded disturbance. Limited dp equals epsilon, and epsilon is a constant. The sliding mode control law of equation 5 can make the system described by equation 1 finally move to the equilibrium point and eliminate the error. That is, limited e equal xe, ye, theta e, t equal 0, 0, 0, t. Drive control. According to equation 3, when a velocity vd, wd, t is input in the kinematics model, the corresponding angular velocities of the left and right driving wheels are WLD, WRD. And then I will describe the experiments. In order to test the effectiveness of the designed control algorithm, MATLAB was used to construct the simulation model to carry out simulation analysis to the ATR control system. Analysis of step signal response characteristics based on ASMTDC and SMC. ASMTDC and the sliding mode control with exponential approach law was used to simulate the control of step signals with initial value of 0 and a maximum value of 20 rad per second. Figure 4 is the step response characteristics curves of the left driving wheels under ASMTDC adjustment. The driving wheel angular velocity started from 0, and the response curve was smooth. The system reached a steady state at 0.375 seconds. B. Tracking control of polyline paths based on ASMTDC. Figure 5a shows the tracking result for ATR of the polyline motion trajectory, and Figure 5b is the corresponding tracking error curve, as can be seen from Figure 5a and 5b. ATR started from the initial position, and the pose error of the ATR could stabilize at 0.71 seconds. It showed that the ASMTDC output was stable, which could make the system quickly converge, thereby meeting the requirements for the accurate and quick trajectory tracking and location of ATR. C. Tracking control of circular trajectory. Figure 6a is the tracking result of the circular motion trajectory, and Figure 6b is the tracking error curve. When tracking a circular path, although the curvature of the path changed at all times, ASMTDC control could adjust the output control in time. and the angular velocity of the left and right travel wheels of the output was relatively smooth, ensuring that the tracking does not depart from the circular reference path. Reality experiment. In order to verify the correctness and effectiveness of SMTDC, a control system based on S3C2440 is constructed, and the independently developed ATR is used as a control object to conduct field control experiments. The control system is mainly to collect IMU information and regulate ATR. The structure of the controller is shown in Figure 7, and the ATR is as shown in Figure 8. Figure 9a shows the results of tracking after ASMTDC was used to control the ATR, as is shown in Figure 9. Apart from the initial operation and the regions with greater curvature variation of reference track, the trajectories of all other regions were smooth. Table 1 shows the error generated when tracking the same trajectory under the same test conditions at different operation speed. As can be seen, when using a combination of cold and straight path as the reference trajectory, the use of ASMTDC to control ATR had better stability and control accuracy. Finally, I would like to make a conclusion with this presentation. In terms of the trajectory tracking problems of ATR, the adaptive integral sliding mode switching function with variable tilt parameters was constructed from the kinematics model and based on the function. An adaptive sliding mode tracking control composed of equivalent control and switching control was proposed. The results indicate that ASMTDC can meet the actual needs of ATR field operations. Thanks for your watching and listening. That's my presentation for the paper. If you have any questions, please send an email and I would be happy to answer that.